Earlier, we had a problem about finding the Cartesian equation of a plane, and we had a sort of complicated way of doing it. In this section, we're going to find a much easier way. So, we have this plane, this red plane here, and then we have our point P, and then two vectors B and C stemming from P. Maybe the origin is over here somewhere, it doesn't really matter. But there's this other vector n, which sticks directly out of the plane in such a way that n is, or it meets the vector C at 90 degrees, and it meets the vector B at 90 degrees. And since every other vector in the plane, say this vector here, let's call it W, since every other vector in the plane W is some multiple of B plus some multiple of C, then that means that, well, we have n dotted with W is equal to lambda times n dotted with B plus mu times n dotted with C. And since n meets B and C at 90 degrees, this is lambda times 0 plus mu times 0, which is 0. So that means that the normal vector n is also orthogonal to any arbitrary vector W in that plane. So we're asked to show that for any points x, y, z in the plane, we have that for this vector n, which points straight out of the plane like this, n1 times x plus n2 times y plus n3 times z is equal to n1 p1 plus n2 p2 plus n3 p3. Not a problem. Let's suppose that the point x, y, z is over here. So this point has coordinates x, y, z. Meanwhile, P has coordinates p1, p2, p3. Because we're told that the point P with coordinates p1, p2, p3 is an arbitrary point on the plane. And so that means that this vector W, which goes from the point P to this arbitrary point here, let's call it Q. So the vector, so Q has coordinates x, y, z. Right, so the vector W is actually equal to PQ, which is actually equal to OQ minus OP. And we know that in vector form, this is, so OQ is x, y, z. OP is P1, P2, P3. So this is equal to the vector x minus P1, y minus P2, and z minus P3. Moreover, we have that n dotted with W is equal to 0. So that tells us that n1, n2, n3 dotted with x minus p1, y minus p2, z minus p3 equals 0. And from there it's pretty easy. It's just n1 times x minus p1 plus n2 times y minus p2 plus n3 times z minus p3 is equal to 0. And the results follows quickly from there. And from the way I've written it here, n dot x, y, z equals n dot p, that's obviously another way to write this exact same equation. So you didn't even need to combine it into a single vector like I did here. We could have, at this point, just taken n dotted with x, y, z minus p1, p2, p3, and observe that that's equal to n dots x, y, z minus n dot P1, P2, P3, and that's equal to 0 because n dotted with this vector here, W equals OQ minus OP, is equal to 0 because of this. If you've forgotten what the dot product means, you absolutely need to revise it because we do need it here. Quick reminder, let's say A is the vector A1, A2, A3, and B is the vector B1, B2, B3. Then we have A dotted with B is equal to the length of A times the length of B times cosine of theta, where theta is the angle between A and B. If you were to present them in the same flat two-dimensional plane. So they're three-dimensional vectors, but together they make a two-dimensional plane. So theta would be this angle here. And you can quickly use the cosine rule to prove that this is equal also to A1 B1 plus A2 B2 plus A3 B3. Anyway, back to what we were doing before. So you might wonder, what's the point of all this? Why do we have this n1x plus n2y plus n3z equals n1p1 plus n2p2 plus n3p3? What's the point of that? Well, now we have our Cartesian equation of our plane. N1, so Ni and Pi for I in 1, 2, 3. These numbers are all constant. So they're not variables, they're fixed points. Fixed values. And so this N1 P1 plus N2 P2 plus N3 P3, this is actually just some fixed constant number, which we can call D. So we have N1x plus N2y plus N3z is equal to D, some constant number, and also N1, N2, and N3 are constant. And if we allow x, y, and z to vary, then all of the values of x, y, and z which make this equation true will also be some points on the plane. And any values of x, y, and z that do not make this equation true will not be on the plane in 3 space. Remember, all of this is done in R3. Somewhere we have the x, y, and z axes. Maybe it's over here. So this can be x, this can be y, and this can be z. And then we have our big plane somewhere over here in this 3-dimensional space, R3. Alright, so if we can find our vector n, we're in business. We've got our Cartesian equation of a plane, and it's much easier than whatever we were trying to do before.